A frequently asked question on social media is, how can I get started with Arduino? And I've done the starter kit, but now what? Hi there, my name's Glenn, and welcome to All About Arduino. In this series of videos, I attempt to answer those questions along with some examples, and the examples are follow along, so you can do them at home. We start out with a single LED, then a single button, and combine them and do more things with them, and eventually conclude with a fully working dice game that you can play dice games. In this first video, I begin where the starter kit ends, and I'll show you some techniques that will help you with your projects, whatever they might be, and of course you can just follow along and do my project. If you find this video helpful, don't forget to like and subscribe, turn on the notifications, leave a comment, and look for me on social media or on my website. Okay, so I'll just get started with a few brief slides to sort of explain the outline of this series of videos and my approach to learning. And of course the topic here is how to get started with Arduino, or if you've got a starter kit, which is a good way to start, how do you use that beyond the examples that are provided? The best way to learn Arduino and programming in general or embedded systems is to have a step-by-step approach. It's the same as most learning, just learn it bit by bit. Learn a basic concept, explore it, adapt it, maybe take a couple of examples and merge them together. It also helps to have a project goal, because what that'll do is, from the myriad of stuff that's available, it'll help you focus your attention on the things that you need to learn. So in this series of videos, we'll build this dice game project, and because we have that in focus as our goal, that's the components that I'll focus on in these videos. Of course, if you ever get stuck, seek guidance from mentors or friends or whatever. Google is a great resource if you can frame the question reasonably well, but also online forums such as Reddit. I participate in Reddit quite a lot, so you'll often find me commenting or posting there. If you have a starter kit, I'd strongly recommend following the examples that are in the starter kit. And the main reason for that is that different components can have different pinouts, meaning the way you connect them can vary depending upon which manufacturer supplied the components that you have. And the instructions in the starter kit are most likely suited to the components that are in there, so you can have a better chance of success just by following the tutorial and the wiring diagrams than if you followed one random tutorial online, such as this one. I will obviously say that this one is a bit different because I use very basic components that do have standard pinouts no matter what manufacturer supplies them, and so you are able to actually follow this one without having to worry about different connection details like you might find with more sophisticated devices such as displays and maybe certain sensors and things like that. Anyway, so you do the basic example that comes with instructions. And then I suggest altering it in some way. Like if it's an LED blinking, then try changing the blink rate. Then expand it in some way. So add a second LED and get them to blink alternately or together, or add a second button if it's a button example, and so on. And then adapt the program to do something else. So if it's the LED one, get them to blink at different rates. Or get buttons to do different things with LEDs, or control different LEDs, or something like that. And then finally combine two aspects, or aspects of the two or more components, to get them to work together. And as I said, have a project in mind, because that'll help focus. So in this video, I'll do the basics. I'll introduce some programming techniques that will help make your life a little bit easier, and I'll also provide two challenges for you to try at the end, which will build upon what we do in this video. In the next video, I'll also give you some solutions, or my solutions to the approach to those challenges, and in doing so I'll also introduce some basic concepts which help make life easier for the next sort of levels of programs. And so in the second video, I'll teach about how to expand the number of I/O ports that are available. And so if we look at the final project, you can see there's lots of LEDs. In fact, there's 40 LEDs, there's 7 buttons, which is far more than the pinouts we have on our Arduino, which I think has about 17 or 19, something like that. And so by having this project in mind, we can see we need to focus on buttons and LEDs, which is the topic of this video. And then later on, expansion of I/O, which is this integrated circuit here, or these 5, and that's what the next lesson will be about. Now, this final project is on Patreon, provides some even more techniques that make life much easier for you. But don't worry if you don't want to purchase it on Patreon. Everything that I cover in lesson 1 and lesson 2 will be enough for you to build this. Even though I won't do the full build, it certainly shows all of the concepts that are required, and you could go on and build this as a challenge by yourself if you didn't want to support me on Patreon. I'll just give you a quick overview of how it works. So I plug him in, and basically, if you're familiar with the Artsy or poker dice, that's what this program does. So if I push this red button here, that rolls the dice. Notice it keeps rolling while I hold it down. Then I release it, it'll keep rolling for a little bit longer. So there's some button management things that we'll learn in this one. That one just resets it for the next player. So if I put a hand up, then I can use these buttons here to turn on the little red LED to indicate that I want to hold those, and then when I roll it next time, those ones will hold, and then I can just keep repeating this process to get a hand that I like. Now, in terms of these show a bill of materials that you need for each video. So obviously you need an Uno, you need a breadboard to connecting everything up, you need some LEDs, you need the current limiting resistors, you will need some buttons, you'll need some pull-up resistors. Now I'll show you a technique later where we don't need to use these. You can use a different technique, but you do need the resistor, and I'll explain why. You need this 74HC595 shift register and some sort of display for the final challenges. So I'll let you scroll through these yourself. And that's the full bill of materials. So for the final project, you'll need 40 LEDs, 40 current resistors, 7 buttons, and 5 shift registers. And as you saw from the video, a few breadboards. If you don't have enough hardware, you can actually do this on a simulator such as Wokwi.com as well. Okay, so we'll get started. So what I'll do first is, as I said, start with a common example, and then we'll change the program. We'll add a second one, so we'll adapt it, and we'll change the way that they blink, and then I'll show you a programming technique to simplify your code by factorizing stuff out into sort of reusable modules. And that'll become important because when I create this reusable module, I'll actually just copy and paste it into other programs, and we can just call it as a reusable module. First, I'll show you where the documentation is. So there's Reddit. As I said, I often participate in that. Looks like I've got 4 messages to respond to. But let's start with the built-in examples. So that can easily be found with Google by searching Arduino built-in examples. And we can see here there's a list of examples. And if we click on one of them, so blink is the first one we'll do, we can see it gives you a very good description of what you need, how to wire it up both in a schematic form and a diagrammatic form, and the code, and it gives a bit of explanation about it. So I'll just go back to the list, and if we start up our IDE, which is here, all of the code for all of these examples can be found in the IDE. So I'll put it over here. So if you file examples, and you can see the top group of menu, the menu there, it's got your basics, which is the same as that. Then you've got digital, analog, communication, control structures, and so on. So there's lots and lots of different examples in here. So I'll let you go through those yourself. So you can either select the example that we're going to work on here, and it'll load it. So I can select basics and then blink, and that'll open a new window, so we can get rid of that one. I'll just make it a little bit taller, so we can see if I click on blink over here, then scroll down to the code, there it is, and then go back, we should see it looks remarkably similar because it's the same. Okay, so this is our blink program. Now also when you get a new Arduino, it'll have a Blink program loaded on it, so you won't have to do anything if you have a brand new one. But if you've been doing exercises, you might have something different loaded on it, and so therefore we will need to upload this. So if I just plug him in, right, so you can see here there's an LED that's blinking, and that's what the Blink program does. But as I said, you might have loaded a different program on there, and so we don't. You might need to reset it. So again, best just to load that one up so we're at least working with the same base. Now, before we do any wiring, I always recommend that you power it down. So we'll unplug our cable. And the first thing we'll do is connect up the ground. Now I'm going to connect it up slightly differently to the diagram that's shown here, and that's mostly in anticipation of the fact that I'm going to add a second LED shortly. There's a tutorial that I wrote that I've put on Reddit about how breadboards work, so I'll put the link in the video, and you might want to have a look at that. But basically there's a row of all of these holes here where you can put components in it, and then underneath the board there's electrical connections. So along these two edges there's a row of connectors, so all of this bottom row here is connected to one another, and all of this second row is connected to one another, and that's indicated by this red and this blue line, which I'll probably make it, oh there we go, that's much better. That's indicated by this red and the is it blue or black? On most breadboards it's blue, but it looks like it's black here. And it's the same across the top here. This top row is all connected, and then this bottom row is all connected. Now you can use this for anything, but it's intended to be used for power supply. So you put plus here on the red side and minus here on the black side, and then same here. And then internally in the breadboard you have these columns. So all of these individual columns are connected in groups of 5. So this 5 set of pins is all connected, as is this 5, but they're not connected across this channel here. So that's a separate section of 5. So the idea is you can put a button across the channel, or an integrated circuit, or a component like the LED, and so on. Let's go back to the schematic. Now in this schematic, what they do is they connect a resistor to pin 13, and then the diode to the resistor, and then, sorry, the diode to the resistor, and then the other side of the diode to the ground. So it doesn't matter what the order is in this case. We could put the resistor at the top and then the diode, or we could reverse it. Now I'll do it this way for the first one, and then I'll do it the other way for the second one, just to show it doesn't make any difference. So the first thing I'm going to do is I'm going to connect a black wire. Again, it's good to have some wire colouring conventions, so black for ground and red for positive voltages. So I'm going to connect this one into the ground pin on the Arduino. So hopefully you can see that's connected into the ground there. And then I'm going to connect it to this blue bus, or the black one being the negative bus. So I'll use this for all of my ground connections for all of my LEDs. Now the next thing I'm going to do is connect the LED to the ground. Now notice that the LED has 2 legs, and hopefully you can see they're different lengths. That's to give you an indication as to which way around it is. Now LEDs are one-way streets, so power will only flow in one direction. So the short leg is the cathode, and that needs to be connected to the ground side of the circuit. So I'll connect that up. So the ground side, or the short leg, plugs into this connection, this bus on the side, and then the long leg is going into the circuit board. Then the next thing we need to do is connect a resistor. So this is a 470 ohm resistor. The coloured bands, which are very hard to see, tell you what the rating is. So that, again, there's charts online that you can look up for that. So now I'll connect this resistor. So I'm going to make sure that one of the legs goes into the same column that the LED is in, and then the other side just plugs into this, looks like row 8 on the board. And then finally, we need a hookup wire. So I'm going to use this yellow one, simply because I've used a yellow LED. So I'm making sure that goes into the same column that resistor is on, and according to our circuit diagram there, that plugs into pin 13. So there's our circuit completed. You can see the yellow wire going to pin 13. Now for these internal wires, it doesn't really matter so much what colours you use. The main convention is power is red and ground is black, but it is handy to use colour coding, and you'll see that in the final project where I colour code the different types of connections for the various bits. So let's give that a try. With a bit of luck, we won't have to do anything because this already has the blink program installed on it, and as you can see, the LED is blinking away quite happily. So success. If you found that wasn't the case, then we can go back over here. Just make sure that you have the right port selected. So I have two. This is doing something else, so I won't select that. And then this is the one that we're working on. The easy way to figure that out is unplug it, check the ports menu so we can see we only have COM30 here right now. Plug it in, recheck the port menu, and we can see the new one is COM13, and it's just automatically selected that because that was what was selected last time. Then the last thing you need to check is that you have the right board type selected. So Arduino Uno, you might have all the boards listed here. I've got a few different categories, so I've got a sub menu, and there it is, Arduino Uno. So with that, we can just upload it. So you can click this little button here, or you can press Control U. Okay, and lo and behold, the LED is blinking. Not much of a surprise because that's what it was doing before. Okay, so I said we can change the blink rate. Let's have a look at the program code first. So you can see here there's two main functions. These things here are functions. They perform a function and finish and then just return to whatever called them. So nothing much is of excitement here. You can't see things being called or whatever. We'll look at that shortly. But there's two main ones that Arduino use. One is called setup, and as its name implies, you set things up in that. And then the other one is loop, and as its name implies, that just keeps getting called repeatedly in a loop. So it'll do the things inside the loop over and over and over again. Now, functions are bound by these curly brackets. So you can hopefully see there a little bit better, they're curly brackets or braces. So when you click on the brace, it'll highlight the matching one. So we can see that's the bounds of this function. Similarly for the loop, that's the bounds for that. And then what these are doing is these are actually calling functions which we don't see. They're sort of provided by Arduino in what's known as the HAL or the hardware abstraction layer. This one is setting the mode of a pin. And it's specifically setting the LED built in, which just happens to be pin 13, which is why that LED blinking or LED connected to pin 13 is working. And we're setting as an output, so we can turn it on and off. The alternative is a type of an input, which we use for buttons. And in the loop, which happens over and over, we write to that pin, the LED built in, or pin 13, and we send a high, which turns it on. We delay for 1000, which is 1 milliseconds. So 1000 milliseconds is 1 second. Then we set it to low, which turns the LED off. And then we delay for 1000. So another 1 second. And then we just repeat that. So on, delay for 1 second, off, delay for 1 second, on, delay for 1 second, off, delay for 1 second, and so on and so on and so on forever and ever and ever, which is what it's still doing. Okay, so let's change the delay rate. Let's make it blink twice as fast. So the way I can do that is change it to 500. So instead of delaying for a full second or 1000 milliseconds, I'll just delay for 500. So that'll blink faster. Re-upload it. And we can see it's blinking faster. Of course, we can make it blink slower or even faster again. Let's try changing it to 1/4 of a second. Upload, Control U this time. It's another way of uploading. Okay, so hopefully you can see it's blinking a lot faster than what it was. Yay, that's very exciting. Maybe not so much. It's certainly a great feeling of relief once you get it working first time, because it's a major achievement for your first go. Let's try adapting it. And so what we'll do is we'll try adding a second LED to it. And we'll continue to use this sample program. We'll just adapt it. So as I said, disconnect the power before we start wiring things up, and that's to provide some safety. And also, as I said, if we just go back to the circuit diagram, I did say it doesn't matter which order we put these things in. So currently I've got the LED connected to the ground. This time I'll connect the resistor to the ground. And there we got the resistor connected to the ground, and then the other side of the resistor goes into pin 15. This time I'll connect a green LED, and again I've bent these to make it a little bit easier to sort of get it to stretch across a wider span if I need to. It's perfectly valid, but it's a good idea to keep one leg short and one leg long, like it was in the original one, so you know which way around it is. There's a couple of other indicators that tell you which side the cathode is, which is the ground side, but the short leg is the easiest way to do it. So I'll make sure the short leg connects into the same column that the resistor appears in. And then the other side of the LED, which is the positive side or the anode, is in column 18. So I'll connect a wire up to column 18. And where should we put it? I think I'll just put it next door. So that'll be in number 12. So now I've got the yellow one in 13 and the green one in 12. And so you can start to see why color coding is useful, because now I know that 12 is the green wire, which I've connected to the green LED. So in this trivial example, that's not terribly important, but you'll find in the future, if you use color coding, particularly the red and black for power, you might save yourself from some disasters like short circuits. Okay, so I'll plug him back in, and our yellow one should start blinking again. Yep, because we didn't do anything to that, but of course the green one isn't doing anything because there's no code in there to cause it to do something, to cause it to do anything. We need to basically repeat what we have here, except we need to do it for pin 12. Remember I said LED built in as pin 13, so I'll copy and paste that, and we change that to 12. So just like pin 13, we need to make it an output. Just like pin 13, we want to turn it on, and then we want to have our little delay. I think I'll stick with 250 milliseconds. Obviously you're free to change that around. And then we need to turn it off. Oops, 12. So I'll upload that. Again, Control U, which is the same as clicking the upload button. We can also, I think there's a menu function here somewhere. Yeah, Sketch Upload, there it is. You can choose that as well if you prefer. All right, so it's done it. And look at that. Both of them are blinking in unison. Now, because our code outputs are high at the same time for both pins, they're both on at the same time. And similarly, we output a low at the same time, so they're both off. Now we could alternate it. So when we turn 13 on, we can turn 12 off by setting it at a low. And then when we turn 13 off, we can turn this one on by setting it a high. Also, we don't have to use this LED built in. I just happen to know that it's 13 because it usually is on Arduino. We could type in 13 because that's the pin number that the yellow wire is connected to, 13. And it'll still work. We'll look at some of these because it's convenient to use constants like this to sort of represent different things, because later on when we look at particularly the more complex project being the full game, sort of 13, well, what does that mean? But if you give it a meaningful name, then it's much easier to follow what the code is doing. Anyway, that's uploaded, and so now they're alternating, which is as we would expect because we're setting different outputs. Now I'll slow them down. I'll set it back to 1000. And then the next challenge is going to be, can we get them to blink at different rates? So can we get one to blink twice as fast as the other? Well, that's going to start getting a bit complicated because we sort of need to have much more complexity and figure out what our delays are going to be. So, for example, we might have both of them on for half a second and then turn one of them off, and then after half a second turn the first one off and then the second one on, and then after half a second turn them both off and then sort of reset. And that's for just like an even multiple of 2. If we had something that wasn't a multiple of 2, like we wanted one to be 150 milliseconds and the other one to be 700 milliseconds, then that makes it much, much, much more complicated and we have a huge amount of code. So a much better approach is to use a different example. Let's just quickly go back to the documentation page. So I'll expand the digital one, so that's another way we can navigate through here. This time we'll be looking at the blink without delay example. So this gives a bit of a description about the problem with using delay, and that basically is that when you call this delay thing, everything stops. Essentially the system freezes, you can't do anything else. And so we need to have a different alternative for all but the simplest of programs like this one. And that's a technique that we use to blink an LED without the delay. So have a read of the description in your own time, but this shows a way of doing it. So we're using the same circuit. I'll just continue to use mine because it does the same thing. Again, as I said, there's lots of different ways of hooking things up and achieving the same result, just as there's lots of different ways of programming things and achieving the same result, which is why I'm starting out with these reference diagrams. Okay, so and then it shows the code. So it immediately looks a little bit more complicated, but I'll walk through that. So again, you can copy and paste from here, or you can open up your IDE and go to examples. Remember, it was in the second group, digital, and there it is there, blink without delay. So I'll just open that. So there's a bit of comments in here that also describes, where you can find the information on how to wire things up. They don't always have that. It depends upon the complexity. But we can sort of ignore that. I should have pointed out that anything that's between this /* or /*, and this */ is a comment, and it's basically ignored. That's just helpful information to us. And also these // that means the rest of this one line. So it's a one-line comment. Again, that means the compiler will ignore that. That's just helpful for us. So we'll start with this first. I'll upload it. And we should see that nothing changes. It'll just blink the LED. Oh, I guess it won't blink the green one anymore. Just the yellow one will blink because that's the LED built in, and it's blinking at the 1 second interval. So how's that working? Well, let's start with our setup. That's exactly the same. We're outputting to LED pin, and then we're setting it to output. So one thing that's slightly different is it's using this LED pin here. So what they've done is they've actually declared a variable up here. This is a global variable because it's declared outside of anything else. And they've set this thing called LED pin. They've created a variable called LED pin, and they've initialized it to LED built in. So effectively this is saying pin mode, LED built in, output. Now, did they need to do this? No, because it's never going to change. In fact, they've even preceded it with the word const, which means that it won't change. And then we have in our loop, we have this slightly more complicated bit of code. And there's a few things that are going on here. We can see here there's a digital write, and unlike the previous example, I'll just open up the original where they hard code a specific high or low, they're outputting this LED state. And what they're doing back up here is they're saying, well, if the current state of the LED is off or low, then we want it to now become high. Otherwise, it was high, so now we want to set it to low. So this has the effect of these sequential lines of code. So here it sets it to high, so the next thing we want to do is set it to low. And then when we come past here and come back up here, it is low, so we want to set it to high. So that's effectively what this is doing for us. This time it's actually changing the contents of a variable called LED state, which also is defined as a global variable. Note that it's not const this time. That means it can change. It's not a constant value, it's a variable value. And they start out with low. So that's all well and good. It keeps changing. That's great. But under what circumstances does it change and get written out? So again, we can click on these little braces and we can sort of see where the function boundaries are. So this bottom one here is the entire loop. So that's what's executed in the loop. And then this digital write is inside this one. And we can see here the matching brace is this if statement. And it's doing this little subtraction and comparison here. So what's this doing? Well, if we start with this, this is initializing a variable called current millis to the result of this function millis. Now you can look at the documentation. If you double click it and then you do find in reference, it'll open up a web page and it'll hopefully tell you about it in various languages, so you can choose whichever language you like. It didn't work. That's disappointing. That used to work. If we go to the top level and we go to programming and then we go to language reference, view all, that used to work. That was a handy feature, but now it doesn't. But somewhere here we see millis, and it gives you a bit of an overview of what it does. The key thing here is that it returns or provides to you the number of milliseconds passed since the program started. So it's kind of a timer. It tells you in milliseconds how long your program has been running. So this is telling me how long my program has been running for. So that's an interesting thing. So what I can do is I can say, well, okay, what's the starting time? Well, we'll just assume the starting time is 0, which is what this previous millis is doing. So we'll just assume the starting time is 0. So when this says 1000, that means 1 second has gone by. So what we can do is we can do this here. If we get our current time, so let's just say, for example, that is 1000, and then subtract the previous time, which was 0. So that's 1000 minus 0 is 1000. If that's greater than or equal to our interval, which is set at 1000, then we'll do the stuff that's in here. So we'll do this stuff. Note that that stuff was including looking at the current state of the LED and swapping it over and then writing it out. Now the other thing that it does here, which is very important, is it tracks what the previous millis was. So we're now at 1000 milliseconds, or it might be 1001, might be 1002, it doesn't really matter. The point is that it's more than, this subtraction is more than our interval. So what it'll do is it'll record our previous millis. So let's say it was 1002 for whatever reason. So we'll keep going through and we'll just keep executing this. We'll keep checking how long the system has been running for, and eventually it'll get to 2002. So we'll do the same subtraction. 2002 minus 1002 is greater than or equal to our interval, which is 1000. So therefore we'll do this again. So we'll remember the previous time. So now it'll remember 2002. It'll check the state, swap it over, and then output it. And that's why it blinks the LED. So let's see if we can make it do both of them and then change the interval. But before we do that, I'll just speed it up. So our interval here is the interval for which we blink. So if I change that to 250, then now our calculation will be, what is the current time minus the previous time, and is that more than 250 milliseconds? So basically saying if 250 milliseconds has passed by, remember the current time so we can check for the next lot of 250 milliseconds that have passed by, alternate our state of our LED, and then output it. So I'll upload him. And there we go, and hopefully you can see our LED is blinking much faster. So let's try and get two of them blinking at the same time. Now the easiest way of doing that is just to replicate it. So first of all, to keep the amount of code we're looking at lower, we'll just get rid of all of these comments. Because we're going to have a second LED, I need to have some way of tracking which LED I'm going to talk to. So what I'll do is I'll create this again and I'll make it 12. But now we have a problem. We have two variables with the same name. If I try and upload that, it'll give me an error. And there's the error there. So LED pin 12, LED built in. So it's confused. You can't have two variables with the same name. So what I'll do is I'll call this one 0, and I'm deliberately picking 0 even though your intuition might be to make it a 1. And we also need to keep track of our two LEDs, because if we do blink them at different rates, they're going to be at different states of on and off at different times. So I'll do the same thing here. I'll call them state 0 and state 1. Again, I'm doing that deliberately, because later I'll introduce a technique called arrays where we don't have to have these duplicate definitions, and they'll also use 0 and 1, but in a different way. So again, if we do blink them at different rates, that means they're going to change state at different times, so we need to track the different times. And similarly for the interval, we might want to have two different intervals. So for now, I'll just leave them all the same. The only difference will be that I have 12. Actually, I might change this one. I might make this one 333, just to give it a different time. Now we need to set both to output as before. Now, do we need to duplicate this one? Well, not really, because there's only one time. We're using these other variables up here to track when was the last time we checked and has enough time gone by before we do something. So we don't really need to duplicate that. One time is good enough. I mean, if it's 200 milliseconds since system start, it's 200 milliseconds since system start, no matter what. But I will duplicate these for now. And so we need to make sure we copy the whole if block. So what I'll do is put my cursor there and make sure I note where that one starts, so it looks like this is the right bit of code to duplicate. So I'll copy and paste that, and then just apply our naming changes. So this one will be number 0. So that one don't have a 0 because there's only one of those, but previous millis will, and interval 0 will. And previous millis has a 0 and a 1, and this has a 0 and a 1, but in each block we will still use consistent numbering, and then finally we'll output LED pin 0 to LED state 0, and we'll just do the same thing here, except this time we'll use 1. So just quickly, the logic is exactly the same, but what we're doing first is we're checking to see if For LED 0, our time has passed. If so, we remember the current changing time. We alternate our LED and then write it out. And then we just repeat that for number 1. Now, if the time hasn't passed, then none of this will be executed, so nothing will happen. It'll just skip down to the next one and check that. If neither of their times have passed, it just comes down to the bottom here and exits, and then the loop starts all over again. We just keep checking the time until such time as the allotted time has passed to alternate the LED. So let's upload it. Hopefully I haven't made any errors. And we'll see what happens. And of course I've made some errors. And silly me, after explaining there's only one time, I did annotate it. So that should be it, I think. That looks better. And now our LEDs are blinking at different rates. Eventually, though, they might line up. But they're clearly blinking at different rates. I could perhaps slow this one down a little bit, maybe make it 500 or 700, just to try and make them a little bit more odd. And so clearly the yellow one, which is LED built in, or pin 13, is staying on much longer, and the green one is blinking at its own little rate. So you can play around with that and adjust the speeds and sort of see how it looks and get some pretty patterns. Maybe try adding another LED if you want to. This is not the challenge yet, but it might be. And have a bit of a play with that. So next we'll look at factorizing this, because if we had another LED, 3, then we're sort of starting to duplicate this again. And if we had 4, then duplicate it again. Eventually we're going to have 40 of them. So this is going to be a hassle to code it like that. So we definitely don't want to do that. What we want to do is start creating some functions where we basically factorize this code out of here, parameterize it, and then just call that function to do the right thing for us. Let's first of all get rid of that. And we'll cut this. And I'm going to put it above these other 2 functions that I'm using, and I'll paste it there. Now that's a problem. We can't just have code there by itself. It will generate all sorts of weird errors. You can try just doing an upload there if you want to and see what happens, but trust me, it's not going to work very well. So we need to enclose it in a function. So first of all, because my cursor is there, I'll input the closing brace, and then I will insert the opening brace. But you can't have just a block of code like that that's sort of unnamed. So we need to call it something. So I'm going to call it check blink, and I'm going to put those brackets there. Now the other thing that we need to do to declare a function, and that's what we're in the process of doing, we're declaring a function called check blink. You need to give it a return value. Now in this case I'm going to return the unsigned long. I'm going to return the time, and so it's going to return an unsigned long because that's return type of millis. I think it actually said that in the documentation page. Yeah, there it is there. So a millis is unsigned long, so we need to use unsigned long for all our references to anything relating to millis. So that's all well and good. We're returning that value. Not really going to use it for much. Actually, no, we'll use it for much because we do have to remember when we last checked something. Now, the other thing we can provide to a function is some parameters. And so we've kind of factorized this code out, although it's not completely done. But we need to provide the main parameters that it needs to operate on. So one of those is the LED pin, because we want this thing to check whether the pin needs to be changed the setting of the pin needs to be changed to turn the LED off or on. We need to know the previous time that we checked. Unsigned long previous millis. And then the other thing that we need to know is the interval. Okay. Now, if I just compiled that, it's not going to work because these variable names actually correspond to these global variable names. So it'll compile, but it won't work the way that we want it to. What we want to do is use these parameterized variable names. So I need to change all of these back again. So I need to get rid of the one from there, the one from there, the one from here, the one from here, the one from here, the one from here, and then finally these ones. So now we're in a much better state, but we'd have a bit of a problem in that we don't have this LED state. I haven't bothered to pass that in. Now, passing the LED state in place of the previous millis, but that's a different problem because when I call this, you'll see that I need to update my previous millis with the current time if this transition has occurred. So I'll just add that first, return previous millis. So what will happen is if the time hasn't expired, so has not expired, then none of this will happen and the function will simply return the previous millis that it was given. On the other hand, if our time has expired, then it will update this previous millis with the current time, so it'll return the new previous millis, or it'll return right now. Otherwise, the state is the same. So what we can do is we can actually manufacture this LED state, because one of the things that the processor does for us is when we digital write, it will track what the current setting of that port is, or that pin, so we can actually read that back in, which might sound a bit counterintuitive, but you can do that. So I'll create a variable called LED state, and instead of saying digital write, I'll say digital read, and then the LED pin. So please tell me what the current reading is for that LED pin, whichever one it happens to be. So this state would be the same. If it was currently low, then we'll change it to high. Otherwise, it was high, so we'll change it to low, and then we'll output the new state. And we can actually contract this down into a single line, which I might do shortly. And then the last thing that we need to do is call this function, because right now the function's just sitting there. It's not doing anything. It's just in the corner all by itself at the moment. So in our loop, what we'll do is we'll call it. And so we need to use these functions that these variables I've declared previously. So these previous millis 0 and 1, the LED state 0 and 1, LED pin 0 and 1, and then just call the function with those parameters. And we'll upload it. With a bit of luck, it will work. We shouldn't see any change in the function because it doesn't do anything. And of course, we don't need to get the current time there because we're not using it there, but we do need to get it in the function. So I'll pass that there. I could have used the time from the loop and just passed that as another parameter, but I'll just put it. That looks better. And of course, we've got the same situation going. The LEDs are blinking the same, but to prove that it's working, I just swap these around 300. It'd be a bit easier to change, and then 700. And then upload it. And we should see the blink rates just reverse now. So the green one will be slower, and then the yellow one will be faster. Okay, so I'll just open up the previous one put them side by side. And so hopefully you can see that the main thing is in the loop. So what we're doing here is we're sort of factorizing it or modularizing it a little bit. And so when we're reading through the logic of the loop, we've called our function a meaningful name, which is check blink. So we know that has something to do with checking the blinking of the LED, but we don't really care about what it's doing. If we wanted to, we could look at it and figure it out, and we can see that it's pretty much identical to what's going on here. The only real difference is that we're reading the state rather than trying to track it via a variable. And we can sort of follow the logic a bit more, so we can see at a glance that we're checking the blinking of LED on pin 0 according to these parameters, and then we're doing the same thing on pin 1. And so we can use this sort of technique to reduce our code. If we sort of go through that, after a while you sort of start to recognize what it's meaning, and you can sort of figure it out, but it's much easier to sort of figure out what the program is doing. It's blinking two LEDs at different rates, whereas you look at this, you sort of have to study it, and it starts to get a bit complex. So functions are actually a really, really powerful and important tool, and you can do so many things with them. There's lots of different ways of setting them up to have default parameters and variants and things like that. So anyway, that's our factorization. I think next we'll move on to looking at a button, and we'll do some more of this factorization with the buttons as well. Okay, so buttons. Let's just have a quick look at what we'll be doing. So I'll start with the standard example. We'll use this one that's on the Arduino documentation website. We'll look at how to connect it up. And then what we'll do is the example that we do will follow the button press. So it turns on an LED when you push the button or release it. Can't remember, we'll find out. And then when you release the button, it turns it back on, or basically changes the state. So the LED follows the state of the button. And then so what we'll do is we'll try and adapt it so that the press of the button will turn it on and off. So the button press will toggle the state of the LED rather than just follow it. Then later on we'll merge it with the blink. We'll add a second example. We'll look at an important technique called debouncing. I'll cover that a bit more, but basically it's to make the button presses a bit smoother. We'll use the debouncing the button and the LED to affect the way the LED works. And again, we'll go through this factorization process. First, we'll look at the documentation. So again, starting here at the built-in examples, we can just go straight to it from the URL on the PowerPoint. We want to do this one, how to wire and program a button. And as you can see, it's got the same sort of structure. It's got the circuit on a breadboard in a sort of diagrammatic or pictorial fashion, and then it's got the schematic. And so we'll set this circuit up. Now, in the previous example, which was the LED, I did say it doesn't really matter which order you put the resistor and the LED in, and in this case that's true because there's really just a straight through path and it doesn't really matter what the order will be. But it does have an effect, and so when we look at the button example, you notice that there's a resistor and then there's a component, so this could have been the LED, and indeed I wired one of the LEDs up like this, the LED at the top connected to the 5 volts. That's this one, the green one, and then the other side of the LED went to ground, and then there's the one that's as per the picture, which is the yellow one, where the LED is connected to the ground and it goes through the resistor. Now in this case, there's an alternate path out here, and this is where we read the state of the button. And the side that the resistor is on will make a difference, and we'll try and look at that in the very first example. So we'll wire it up like this first. Now to begin with, I'll just remove the power. And I'll start by putting the resistor in. So this one is a 10K resistor. Again, the coloured bands can tell you what the value of the resistor is. Brown, black and orange. You can get resistors with more bands, and the colouring will be slightly different. So you can find lots of guides online that show you how to read those things. So there I've connected the resistor into the ground. Now the circuit in the diagram doesn't call for these LEDs. I'm going to use them later, so I'm just going to leave them there. It won't affect anything. The code in the example will blink the LED built in, but it'll use 13 this time. So since we've got that connected, we should be able to see the LED action here. Now this is a push button. Basically there's a little metal contact inside there that connects the two sides up. They can be a little bit confusing. A tip is that the diagonal sides are the ones that are operated by the button. In actual fact, it's this side, so this side to this side that's affected by the button, but it's always a safe bet that it'll be the diagonal. Now you should always check that. They might not always be the same, but generally they are. Now a good tip for remembering it is if you look at the spacing of the legs, you can see that that is a little bit more than that. So this spacing is designed so that it can fit across this little valley here in the middle of the circuit board. So I don't know if you can see that, but it perfectly fits across. If you twist it this way, it doesn't make it. See, it's falling a bit short. Let's try zooming in there. Yeah, so it's falling a bit short. Whereas if I put it this way, then it fits perfectly across. So that's the correct orientation. Now if you put it in the middle here like that I've seen some people do, it'll fit in either orientation, it'll meet. But then the problem will be that, which is the correct way for you to wire it up. It could be that you've short-circuited it. So the best approach is to bridge it across the valley, because it should only go the correct way. Okay, so we put that in, and yep, so what we have here so far is we've put the resistor. It's connected to one side of the button, and the next thing we want to do is connect this wire to pin number 2. So that's from the connection that's between the resistor and the button. So that would be somewhere here. Here's the connection from the resistor to the button. So you want to connect that up somewhere there. So I'll put him in the middle. So just there, and then pin number 2, which is that one. Should perhaps zoom out a bit more so we can see what's going on. So yeah, that's pin number 2, the blue wire's in pin number 2. Now the next thing we need to do is connect up the power. So we need to have a +5, so I've already connected up a red wire here which connects to the +5 on the Arduino, and note that I've connected that up to the red bus. So now we can start to see the benefit of the color coding, that red goes to red, black goes to, well, blue, but we know that that's the ground. So if ever we saw a situation where the black was touching the red like that, then that's a problem. It would probably destroy something if we did it that way. We always need to have something in between them. And then finally I'll connect the power up to the button. So as I said, it runs across diagonally, but reality is side to side, so it's safe to connect it up like this. And collect that to the plus side. So just check the wiring. Red is to red, the blue is our signal, the resistor's going to the ground, so that looks all good. Let's push them out of the way. All right, so let's load up the example. So here's our previous program examples. Again, they'll be in the same menu structure as the documentation. The names are slightly different, so in this case it's button. And if we scroll down, should see that the code pretty much matches up. So we've got this button state 0, got our setup with 2 pin modes, and we've got our loop with the same code. So just upload that first, and we'll see what happens. Now a common mistake that I see is people don't include this resistor. I'll explain why that resistor is important, but it is important to have the resistor. This one's a 10K resistor, which is much higher. It's about 50 times the power, or it's actually about 20 times because mine is a 470 ohm resistor here for the LEDs, or it's 50 times the resistance. But this one serves a different purpose. This one limits the amount of power that goes through the LED to stop you from damaging something. So people often omit this one as well. And generally it'll work, but you are putting a strain on the MCU or the LED, but in this case it's more likely the MCU. In this case, the resistor is performing different functions. It's giving me a positive signal when I'm not pushing the button. And as I said, we'll look at that a bit more closely later. Okay, so that's uploaded. With a bit of luck, if I push the button, the LED should light up, but it's not. So that means I've done something wrong. What have I done wrong? Oh, I didn't plug it in. Okay, so it didn't upload. It says problem uploading. Silly me. So just try that again. So we can see the LEDs have stopped blinking, which makes sense because we're not doing anything to blink them. And then I push the button and sure enough it lights up. If I release the button, it turns off. Push the button, lights up, release, off. Push, on, release, off. So isn't that exciting? Okay, so as I said, the position of the resistor will make a difference. So notice that here, if I push the button, it turns on. So just remember that. So just unplug the power since I'm rewiring it. I think what I'll do is I'll put the resistor across here like this. And before we had the resistor, just bring the diagram back, there it is there. The resistor was connected to ground. So what I'm going to do now is connect the resistor to +5. So I can do that by putting that wire in there. And then I'll connect the other side of the button to ground. So rather than the other side of the button going into +5, which is where it was before, I'll connect it to ground. So I use this black wire for that. So again, I've got red to the positive side of the resistor, then we're taking our feed out, and then black goes to ground. So that's all good, all the colours are matched up. Plug him in. Now this time we notice that the LED is on. And then when we push it, it goes off. Release, on. Push, off. Whereas before it was push on and release is off. So it's inverted it. So in this case, the position of the resistor does make a difference. So what's going on there? Well, let's have a look at this. Okay, so this is a little circuit emulator. I'll just stop it and reset it. And what we have is the representation of the Arduino on this side, and this is our input 2 here. And then on this side is our circuit that we're testing. So we've got the resistor at the bottom and then the button at the top. So when I start it, we can see that current is coming out of here. And so when current is coming out, that means that the digital pin will read as a low. If I push the button, then current is flowing into the Arduino, so that means the digital pin will read as a high. And if we look at our code, that's why the program is initially working the way it was. So current is just flowing out, which means that when we do this digital read in our loop, it'll get a low. So the button state will be low, and therefore it turns the LED off. When we push the button, now the current is flowing into the Arduino. So now when it does the digital read, it'll register that the button state is high, so therefore it'll turn the LED on, and that just keeps going on. As I modified the circuit and put the resistor at the top, now we can see that the current is just flowing in straight away. So what's happening there is that when we do the digital read from this signal here, we get a high. So therefore it turns the the LED on by default. Now, when I push the button, there's another path for the current to flow, so it registers as a low because the current is now flowing out of the digital I/O pin. So now because the button is pushed and the pin reads as low, it turns the LED off, which is the reverse logic. So this resistor is called a pull-up resistor because when there's no circuit here at the switch or the button, it's pulling the circuit high or pulling it up, and so therefore we by default get a digital read that says high. With this one's called a pull down resistor because it's pulling the circuit down to ground. And so when the button's not pressed, it's sort of sucking the electricity or the current out of the GPIO pin, and so it registers as low. And then when I push the button, there's an alternate path, so now it becomes high because the current is able to flow through the switch and into the Arduino, so it registers as high. So hopefully you can sort of see why this resistor here is actually important, or in the other case the one at the top. But it's important to have a resistor here, because if we don't have a resistor, this one, then you can see that the current is flowing through, but it's kind of nothing's happening here. So that's sort of indeterminate. Is it low or is it high? You can't tell because it's indeterminate. If I push the button, then now we have a clear path. So there's current flowing into the Arduino, so I can clearly say that's high. But when I let it go, it can't. And in fact, what happens is, this is what we would commonly refer to as an antenna. And so what it'll do, and this simulator doesn't really simulate this, is it'll actually receive random signals. So you can actually do things, if all of the conditions are right, you can actually do things like turn the button on or turn the LED on or off just by sort of moving things near it or waving your hands near it or whatever. So that's not a good circuit. That's called a floating input because it's not connected to anything in this situation. Now you could do something like have a button here and a button here, and that would give a determinate signal, but there's a transition state where it's indeterminate. But that would also be dangerous because if you put a switch here, that's a zero resistance circuit, and that's a short circuit, and you're likely to damage something. So don't do that unless you clearly know what you're doing, and never have both of them pressed at the same time. But you just generally avoid doing that. You want to have this type of setup where there's a resistor between the +5 and the ground, or some other component that does provide some resistance. Okay, so that's the theory. Let's see if we can't make this so that the button toggles rather than follows the LED. To make it toggle, we kind of need to adopt what's going on in this blink circuit. So what we need to do is when the button is pressed, we sort of need to say, well, what's the current state of the LED? Invert it and then write it out. So later we'll copy and paste this. But first we need to sort of modify this so that we can detect when the button is pressed. Because right now, all we're getting is what is the button state right now. What we want to do is say, when did that state change from pressed to not pressed? Now at the moment my circuit is wired as a pull-up because the resistor is connected to the +5 volts. So that means the not pressed state is high, which is why our LED is on. So to press it, what's happening is it'll previously be high and then it'll be low. So how can we do that? So the first thing we probably want to do is track the previous button state. Now, because it's a pull-up resistor, when we first power up, the previous state will be high. So we'll initialize it to high. Now we'll still read it as we did before, but what we'll do is put an if here. If button state is not equal to previous button state, and this is the key. So what's the current state right now, and what was it when we last checked? And if it's changed, then we want to do something. So what do we want to do? The first thing we want to do is we want to remember okay. And then the next thing that we want to do is say, well, if the button has been pressed, so what that means is if it was high and is now low, then we want to actually toggle the LED. If it's the other way around, if it was low and then it's high, which means we released the button, we don't want to do anything. We only want to do something when the button is pressed down. So if the button state is low, now we want to actually toggle the LED. So we want to do this. So I'll copy this and then paste it here. Now you can sort of see the indenting is not very good. It's a good habit to sort of indent things that are under the control of something else, because that just makes it a bit easier to read. So we can sort of see that this if statement, all of this stuff here is sort of under the control of that if. We can see that also by clicking on the braces, and it highlights the next one, but it's sort of annoying and awkward to have to do that. It's much easier if we indent things. So what I can do to indent this fairly easily is just select the bit that's under the control of this if, and then hit the tab key, and then it just indents it nicely for me. Okay, now we don't want to do any of this stuff because this is the old logic which was just following the button. So now what we have is we read our button state, we compare it to what it was previously, and the previous state on startup is high. So when this first starts running, our button with our pull-up resistor will be high, so this will be false. It'll be is high not equal to high. Well, that's false, so it basically just drops down out to here. But eventually we'll push the button, so now the button state will be low, which is different to the previous state, which was high just as a fraction of a second ago. So we'll remember that for next time. We'll remember that we've seen it now is low. And then we check to see if the button is low, and if so, we'll just toggle the LED as per what this blink code does. Later, we'll release the button. So, before that, while we're holding the button down, we'll just keep getting lows here, and because we remembered that it's now low, this will be false, so it'll always just drop down to here. Eventually, we'll release the button. And so what will happen is now the button state will be high, whereas previously it was low. So remember that we've now seen the button turn high, but then we come down to here. So when we release the button, the new state will be high. So this won't be true. So therefore it won't do this. And then it'll just drop out here. So all it'll do is remember that now we have a high button state. So we'll just upload that and see what happens. Okay. And there we go. Now I didn't initially do anything with the LED, so it's just gone into the off state. But with a bit of luck, if I push the button, it'll come on. And if I let go, it should stay on. If I push it again and let go, it stays off. Push on, push off. Push on, push off. Now notice that it doesn't work reliably. Sometimes I push it. Now it's not going to do it. Oh, there we go. Now it's sort of following there, now it's stayed on. So it's not sort of working reliably. And the reason that's happening is due to a phenomenon called bounce. So when you make this contact, my finger is like glacial speed compared to the speed that the CPU can read things. And so what's happening is the electrical contacts are sort of slowly coming together, and they're sort of bouncing off of each other as the button makes contact. So you get a couple of false readings. It sort of says, well, yeah, you pressed it and then you pressed it again, sort of within a millisecond sort of thing. I don't know if you can see me pressing it, but sometimes it stays on, sometimes it goes off and on briefly, much faster than I can press it, or it's not responding. That's because of this bounce phenomena. So we'll look at that next, how to make the button presses more reliable and sort of prevent that. So you should play around with that yourself. Just try pushing it, wobbling it around a bit, and see, it's not always one press on, one press off, unless you're really careful about how you do it. Okay, so let's try merging these two programs. Yeah, so we're going to have one LED blinking and one LED toggling based upon this wonderful creation that we've just made. So what we'll do is I will call this one the LED blink pin, and then that one, the LED button pin. Actually, I'll call it toggle pin. Yeah, so that's the one that will be under the control of the button, and we'll make that 12. And the only reason I'm going to make 12 is because we just happen, through sheer luck and coincidence, to have a green LED connected up to pin 12. The button I'll leave as 2, so that's fine. And then we also need to have some variables for the timing. So that's for that blink. So I'll put that one down there and try and just group these things together. But why am I typing it? I'll just copy it from over here. Unsigned long previous millis. So we need one of them. And I'll get rid of this 0 for now. And we need an interval. So again, I'll bring this one over. So what interval should we have? I think 300 is fine. All right, so that's good. The next thing I'm going to do is copy and paste this into here. And then we probably won't need that anymore. So there's our check blink function. That's pretty much going to be the same as before. I don't think we need to make any change to that, but let's see how we go. And then the next thing I'm going to do is I'm going to rename this to check button press. Now we have a little bit of a problem because we don't have a loop, but we'll address that shortly. And I'm also going to move it up to here. So this is just a convention. It's simpler if in C programs, not so much for the Sketch INO program, but it's simpler if you put the functions before or declare them before they're used. I want to make this a generic function, so I'm going to create this button pin thing here. And it's already using the right names, so that's all good. We'll read the button state. If it's not equal to the previous state, remember it. So that's all working. That's fine. Now the setup, we've got this LED pin is output. So we changed the name of that. So that's LED blink pin and toggle pin. Blink pin is set to output, and toggle pin also is set to output. Now, as I said, we do have a bit of a problem here because we don't have a loop function anymore, so we need to recreate that. So void loop, there's nothing special about this, it's just text, so you can just type it in like that and rename them as you see fit. The only requirement is that you do have a setup and you do have a loop, and that they be declared like that with no parameters. So the first thing I'll do is call check button press, and it's my button pin. So that'll just go through exactly like we did before. The only difference is that the button pin is being passed as a parameter. Now, interestingly here, the names are the same. They don't have to be. In fact, I'll prove that. Button pin. So I'll call this toggle pin, which means I'll need to change this one as well. Toggle pin, and of course this one. So when we call this check button press with toggle pin, it will be referred to via this variable name here, so we can pass different values. Just the same as over here, we passed different variables into the check blink and got it to do different things. And then finally, we need one of these. And we just change the various names. So now we have a situation where two things are going on at the same time. We'll just constantly check for the button being pressed, and if so, we'll do this toggling of LED 2. So I think this name is wrong. LED toggle. Digital write LED toggle pin and digital read LED toggle pin. So just do the same thing. Again, I could pass this as a parameter, but I don't really want to. Oh, that one was correct. It's this one. Toggle pin. Toggle pin. Okay, so as I was saying, I could pass that as a parameter here if I wanted to, but I really don't want to do this long term, so I just leave that sort of hard-coded as that pin there, because I actually want to do something different with this function later on. This is kind of a bad programming practice, unless this is how you always want it to work. The idea of modularisation is that if this is checking to do something with the button press, then that's what it should do. And it should return that the button was pressed or it wasn't pressed. It shouldn't just do other stuff as well. As we'll see later, that's what the subject of this loop will be, that we'll check that the button has been pressed. And if so, then we'll do something with it. And if not, we'll just, I don't know, do something else or do nothing. But for now, this is good enough. So we'll check the button, toggle, and then we'll do the blinking if that needs to be. And these things should now operate independently of each other. So we'll just upload it and see what happens. And of course we have an error. LED pin. So I did need to change that somewhere. I thought I would have to. LED blink pin, I think we called it. That looks better. Okay, and so now our yellow LED is blinking, and as before, our green LED is not doing anything in particular. So I push the button, and now it's on. So now the green one is toggling on and off as I push it. Now this debounce problem will still be there. And again, we'll look at that eventually. We'll do that last because that's a little bit more complicated. All right, so let's see if we can't get these two functions here to sort of interact with each other. And what I'll do is I will use the button press to basically affect the rate this LED blinks. So in other words, I'm going to change this when the button presses. So I don't need that one anymore. I'll just put that up there like that. I'll start at the top this time, or the bottom of the code, but the top of the logic. So what I'm going to do is make this so it returns a value that's useful to me. So if the button is pressed, then I want to change my interval. So let's say I start blinking at 500 milliseconds. I'll change to 250. You can put whatever values you like. Interval equals 500. Okay, so that should be good enough. So basically when the button is pressed, I'll check what the current interval is. If it's say 500, then I'll make it 500. If it's if it's 500, I'll make it 250. Otherwise, if it's not 500, then I'll set it to 500. Okay. So the important thing here would be that this value and this value is the same. So it doesn't really matter what you start with. If it's not 500, then it'll set it to 250. Sorry, if it's not 500, then it'll set it to 500, and then next time through it will be 500, so it'll change to 250. The next time through it's 250, so that's not 500. But we'll start it with an appropriate value. So, well, in fact, let's just leave it like that and see what happens. 300. Okay, so that's probably enough for that. Later I'll look at how we can actually reduce that down to one line. That's a little bit wordy. Some people prefer this because it is wordy and it's much clearer what's going on, but we can actually simplify that to one line, which other people might say that's more efficient, but it's a little bit trickier to read. But we'll cross that bridge when we come to it. Now we don't want two LEDs, so I'll start getting into some of these comments as well. I think we can call that LED blink pin, so that's fine. The interval is fine. Now we may have a problem up here, yes. So because this interval is declared as a constant, if we tried to compile it now, it's going to give an error. It's going to say we're trying to change something that's a constant, so we don't want that to happen. So we'll just take that const off of there. Now the main thing we're going to change here is the check button press. This blink thing should be okay because it already takes the interval as a parameter, and so hopefully it'll do the right thing. But as I said before, it's not great that we're doing this stuff in here. Where does that finish down there? It's not great that we're doing this stuff in here, because this is about checking button presses, not about doing stuff with LEDs. So some of it is okay, and we'll retain some of it, but certainly this stuff here about writing to the LED is not something that we want. In fact, that's pretty much mostly what we want to get rid of. So I'll just simply delete that, and I'll say, well, if the button state is low, then I'll return true. Otherwise, just always return false. So what we're doing is we're reading the button state, we're checking to see if it's changed, and then remembering that. And if its now press is low, meaning we've pressed the button, we'll return true, saying yes, the button has been pressed. Otherwise, we'll always return false. Now, there's a little bit of a problem here because we've said that the return type is void, which means we're not returning anything at all, which was the case originally. But now we are. So it's a bool or a boolean. Either is okay. Okay, so we'll return that true or that false. And then I think the rest of it is okay. So the LED blink pin, we don't need this one anymore. Got the blink pin, the previous value is 0, the button state is 0, the previous button state is high. Okay, so I think that's good enough. Let's try uploading it and see what happens. Now what we should see is the yellow LED blinking and the green one not doing anything when we push the button. So there it is, it's blinking now. If I push the button, you can see there it's blinking faster. If I push it again, it's blinking slower. Okay, so now we've successfully done that. So now we actually have a function which is check the button press, and when it's pressed we get a true, so it changes the LED blink rate. Okay, so I said that we can actually simplify this, and if we think about just simple arithmetic, what is this doing? Well, I'll actually write the formula first. I think it's easier if we do that. Now, it will be important that the starting interval is one of those, but we could get away with that, but I'll start it at 500. So initially our interval will be 500. Now, what happens when the button is pressed? So we'll do this calculation. We'll set the interval to 750 minus the previous interval. So this is okay. It does that calculation. It figures out the result, and then once it's finished figuring out the result, it'll put it into here. So there's no sort of real conflict there. If you're a pure mathematician, that's sort of not a good formula. That's not possible. Interval can't be equal to that. In computers, the equals is more of an assignment rather than a statement of fact. So this sort of statement is okay, even though it might be a bit counterintuitive if you're a purist mathematician. But what will it do? So initially the interval is 500, so it'll do 750 minus 500, which gives me 250. So it'll put 250 into the interval. Next time around the interval is 250, so it'll do 750 minus 250, so it'll put 500 in the interval. So this has the same effect as this if statement. That's a little bit less obvious, but that's what it's doing. And the way you work this out is if these are the two intervals that you want to use, 250 and 500, then you just simply add them up to get this value. So 250 plus 500 is 750, and then that interval just switches between them. So it could also work with other values. So for example, you could use 150 and 600, for example. That would work the same way. So 750 minus 600 is 150, and then 150 minus 750 is 750 minus 150 is 600, so it works the same way. But the key thing is that this number here has to be the total of the two. And obviously this will only work for two values. If you want to have more values, which we'll look at later, actually maybe that'll be the challenge. We need to take a different approach, but this is good enough for this one. So let's do that. Let's start with 600. Well, I'll start with this. No, we'll just go straight to 600. No, we'll start with this first. So I'll leave it like that. We'll upload it, and we should see that it behaves the same way. Alrighty, so our LED is blinking slowly. Push the button and it's still suffering that bounce problem. There it is now, it's blinking faster. Now it's slower and then faster. Now if I change the initial value to one of these, let's say I make it 600, you should see the change in dynamic. So I'll upload that. Okay, so it's hard to tell because it's not much slower, but if I push the button, that's definitely a lot faster now. Okay, so it's hard for us as humans to judge the difference between a 500 and a 600 millisecond delay, but we can definitely see the difference between those two. The faster rate, that's much faster than the 250 millisecond delay. Okay, so let's tackle the bounce problem. Most of the things we'll need to change will be in here as we add some logic to this. Basically, the approach is going to be that we will sort of have an official state of the button, a current state of the button, and that's what we have in these ones, the button state and the previous button state. And then when it changes, we have a new official state. But we'll have an interim state or a proposed state, because the idea of the bouncing is that when you push the button, it momentarily makes contact and then breaks and then makes contact again very, very quickly. And that's why we kind of got like a double press. So when we notice that there's a change, we'll sort of have a proposed change, and then after a period of time, then we'll say, yep, now we're satisfied that it's actually settled down, and that's the official state that we want to track. So what I'll do is I'll declare a temporary variable in here. So note that a variable that's declared inside a function only has a life and it only exists for the life of that function. So when this function exits, that variable reading will disappear. That's unlike these ones up here that are permanent. So this one here, button state, is sort of registering what our official button state is right now, and that will last because that's declared outside of a function. Where's our function gone? Oh, here it is. Okay. So if the current reading is not equal to the previous button state, then what we want to do is basically track what the time is now. Because remember, what we want to do is just allow a short period of time to go by before we decide, yep, everything's sort of stable now. And then we'll remember what we just saw. So what we're looking for is that this thing just keeps bouncing. So as it keeps changing due to the bounce, really what we're going to do is just reset this last debounce time. So what we want to do is, once we get a reading, we want to just make sure that that reading remains stable for a period of time. And that's the bit that we'll do next. So because I've introduced this variable here, I need to declare it. So I do that while I remember. So I put it up here. And we'll also want to have an interval. So it's a little bit like the delay. So there are actually some similarities to this and the LED blinking function. So this can be const because I'm not going to change this. And I think 50 milliseconds is a good enough time for like a starting point. It can vary depending upon the quality of the button and the system that you have, but 50 milliseconds is usually a good time. So that corresponds to 1/20th of a second. So definitely faster than we humans can typically react. So we'll sort of feel that it's an immediate response, even though there will be at least a 20 millisecond delay. So where's our function? Oh, here it is. Now what we want to do is we don't really want to check to see if it's changed, because that's what's happened here. We're checking to see if it's changing, and then we're resetting the time. So what we want to do is just make sure that amount of time has gone by. If millis minus the last debounce time is greater than the So what we want to do is just check that the millis minus the last debounce time is greater than debounce delay. So we're checking to see if sufficient time has gone by to then say, yes, this is an official button state. So now we want to do is actually check that the button state has actually changed, because it could be that it's gone up. So let's say it was pressed and then we release it and then just sort of press it again. So we kind of like momentarily released it incorrectly. Then it's still going to be low. And similarly, if we sort of bump it while it's not pressed, then it'll sort of briefly go down and back up again and still be high. So we don't want to register that as a press, even though we have been tracking that it was low and then it's gone back to high. So what we want to do is just make sure that it has actually changed. So if our reading is not equal to the button state, so this is the official part, so has the official state changed? And again, we want to indent this a little bit more. Then if it's true, then we want to return. But we also want to change this as well. If the reading is not equal to the button state is now officially the current reading. And then if the button state is low, so our official new state is low, then that means we've just pressed the button, so we'll return high. So just in summary, we are detecting if the button has changed its state in some way, and if so, we want to basically start up a timer. And then if the timer has expired, so enough time has gone by, then we're just sort of checking that if the last known reading, so we don't know how much time it's gone up and down, and we really don't know how many times it's done that, but you just want to make sure that the last time that it's been stable is different to the current official state. So it's actually been pressed or it's actually been released. Then we just remember that, so we officially say that now the button is pressed or now the button is released. And then we check to see if the button state is low, meaning it has now just been pressed, then we'll return true. Otherwise return false. We'd basically say nothing's happened. That's at least nothing of interest has happened. But in this case, when the button does officially, after a brief period of stabilization, does go low, then we'll return true. And again, this logic is all dependent upon us having a pull-up resistor. If we had a pull-down resistor, we'd have to invert some of this. This other stuff is probably okay. I'll just get rid of this to make it a bit shorter. And that should be good enough, so we'll give it a try. And of course we have an error. Debounce interval, debounce delay. Which one shall I change? I'll change this one. Oh no, the other ones are called interval, isn't it? Yeah, so I can keep my name consistent. And you have to spell millis correctly as well. Now it's going to be hard to demonstrate this, but it should be that the button presses are much more reliable and you don't get the effect where you push it once and it doesn't actually register. So what we're looking for is that a single press is registering correctly, and it looks like that's much better than before. Even if I sort of roughly stab at it, it's clearly being much more responsive. So you can experiment with that yourself. All right, so you can play around with that yourself. Try maybe switching the resistor back to a pull-down resistor where it was connected to the ground, which is the original circuit in the diagram on the documentation page. But you should get familiar with using it like this, because later I'll show how we can actually ditch this resistor. So in the final project I won't have this resistor on my board. You still need to have the resistor, but it turns out there's actually resistors inside the MCU here, and what I'll do is I'll use the resistors that are inside here rather than actually having a physical component on my board. And so what that means is I won't need this wire here and I won't need this resistor. It'll simply be the button
connected to ground and then into the Arduino's GPIO port. So that just makes the circuit a little bit tidier, and it's in there, so why not use it? But it's clear the reason we've done it this way is to show what this does and how it is important, but we don't actually physically need it here under most circumstances. All right, so I think I'll leave it there. What have we covered so far? So first of all, I said it was good to have a project goal to focus what we're going to be working on, and so that's going to be this game here. And that, as I said, focused us on looking at buttons and LEDs, and then next time we'll look at these integrated circuits to expand our I/O capabilities. In terms of what we've learned, an important one, even though I didn't really sort of mention it by name, is state machines. So if you think about the LED blinking, we tracked what the LED state was, and then we would change it. So that's a very, very simple state machine. Similarly with the debouncing of the button, we sort of had this sort of current state, sort of proposed or interim state, and then a final official state sort of thing. So that's a state machine as it moves through the various stages of its life. One of the benefits of the state machines is these two things is that it allows you to let time pass when other things can happen, and more importantly, it eliminates lag and freezing symptoms, which is what the delay function would do. So it basically allows your project to be much more responsive to inputs. And also I looked at some optimizations where we would refactor code into some functions, and then we could reuse those functions when we're combining them, and just sort of link them together with a very simplistic sort of mainline or loop function that just calls them to do what they need to do. And we didn't really have to care about what they were doing anymore because we had got them working. So we look at a lot more of these sorts of optimizations and making functions and using data to drive the program, a little bit like that subtraction thing for the interval blink program. Okay, so now to the challenges. So yep, there's some homework. Obviously you don't have to do this, but it's good for you to sort of try and expand your knowledge and work out how to make these things work. I'll present solutions in the next video, or at least my approach to doing these things. And so start with the blink program that had the two different LEDs blinking at different rates, and try and add two more and get 4 of them working at the same time. So basically I expect it to work like this. As you can see, we've got the 4 LEDs here blinking at different rates. That sort of looks a bit haphazard. That's because the rates, as it's sort of indicated there, 150, 200, 333 and 500 milliseconds. So they really don't sort of align that well, and so they sort of blink a bit randomly. Don't forget the current limiting resistors, they're very important with LEDs. Okay, so the second challenge will be to build up on the buttons example where we had the one button that was controlling the blink rate from faster to slower. And so what we'll do is we'll have 4 or more different speeds. So what that will look like is this version. So I've got the one LED blinking, and as I press these buttons, it'll slow the blink rate down. And if I press this one, it'll speed it up. And then slower. And then a key thing here will be that when you reach the extreme, so when you're at sort of 500 milliseconds, which is the slowest blinking rate, then pressing slower will have no effect. Similarly, when you're at this rate, the 100, that's the fastest blink rate, pressing faster will have no effect. So don't go past these bounds. If you want to try having more than 4, that's fine. If you want to do 2 LEDs, that's fine as well, but this would be good enough to experiment. And what I'll do is my solution will introduce a technique called arrays, and I'll go through that in my solution, but that's going to be a building block for the next levels of the program. Okay, so the next lesson is going to be about shift registers. So as I mentioned, this final project has 40 LEDs and I think 7 buttons, which is far more than the I/O pins, so it's going to be a problem to connect them up. So we need some help, and that'll be in the form of these integrated circuits, shift registers. So what I'll do is I'll build one module, which is one of those, so 8 LEDs and a shift register, and then as you can see, this module is replicated through the chain. So as I said, once we've done lesson 1 and 2, you'll definitely have enough knowledge to build all of this project, even though the final build will be on Patreon.
Thanks for watching. I hope that was helpful and you get some basic ideas of how to test a few components, get them to work by themselves, then merge them together. So please leave some comments. I'd love to hear how you've gone and any ideas you have. And also consider liking this video, subscribing to my channel, turning on notifications so you'll see new content, and also look for me on social media. Usually I'm on Reddit and or my website. You might also find my introduction to debugging video helpful. That's useful for techniques to help you figure out why things are going wrong or not working the way you intend them to work. And so that can be found on YouTube as well. There's also a follow-along guide of the same content on Reddit and the wiki there. So again, thanks for watching. All of the best with your projects. I'd love to hear how you're going, and see you next time on All About Arduino. Bye for now.